questions about the midterm that's coming up?
How similar would it be to the practice?
So the question was, how similar will the midterm be to the practice exam?
Are you recording this?
Yes. And so the practice exam has 5 questions. One about a recursive function with a helper function. One with using a fold. One with using map and flat map. One with a grammar, and one with modifying SL1. The midterm will have 1 question about a recursive function with a helper function. 1 question with a fold. 1 question about flat map and map. 1 question about modifying a grammar, and 1 question about modifying SL1.
Okay, so we would just use the same fundamental skills.
Yes. So I picked these questions for a reason. So if you can do this thing cold in 70 minutes, you will also ace the midterm. Yes? So there's going to be a question about a recursion with a helper function that will have nothing to do with this question. There will be a question about a fold that will be implementing the same thing as a fold, but something completely different than you have seen. There will be a question about flat map and map that will have nothing to do with this question. There will be a question about a grammar that will definitely not be with concatenating strings. And there will be a question about modifying SL1, and you won't know what it is, but you will know one thing: you will not have to put in the Boolean type. Yes, so of course there will be different questions. I mean, there will be no sense for me to give you the same questions. Yes?
So, if for the question where you have a helper function instead of a function, you make too many unnecessary additions, but it still works.
I don't care. Yes, so the question was, what if your solution is not optimal? What if it does extra work or has extra definitions that you end up not using? I don't care. The other thing to keep in mind is that with the first 3 problems, I would imagine it is in your interest to try to get the thing to compile and to run, because you can just do it in a worksheet and it doesn't really cost you anything extra, and that way you can test that it actually works. But particularly for the last 2, where it's a little bit fussy sometimes, as you know, you could get a Scala error that would take you 20 minutes of back and forth to figure it out. That's probably not something that you would want to do in an exam. You're not required to hand in working code in the exam. I will look at your problem even if it doesn't compile at all, and I will attempt to divine partial credit for whatever. It's helpful for me to have it as a program, because sometimes students will hand in a solution that actually perfectly works, and I just didn't understand how, and then I can quickly run it. So that's nice for me, or I can beat it into shape and then run it if that's what I want to do. But with most of the solutions that you turn in, I will just have look at it, identify that it has the varying parts that are required, and then grade from the rubric. So please do not spend an enormous amount of time in the exam trying to debug something or trying to get something to compile if you find that it's confusing. Move on to the other parts first, and then if you have extra time, sure, then you can do that. But sometimes I see that with students that they're so fixated on getting this thing to totally work, and in a 70-minute exam, that's not always the winning strategy. So the winning strategy is to attempt each problem, to do as much as you can in each problem, and then to go back and drive them to perfection. And you will know what it is that you can do easily and where you have more problems. Just use your time wisely. Yes?
We can save time by making the directory ahead of time.
Well, in fact, I will do that for you. So don't do anything. What I will do is I will prepare in your repos a folder called midterm, with the project set up correctly, so you don't have to do any of that stuff. So it'll already have the SPT build and everything. It'll have a source main Scala. It'll have 5 files called problem 1, problem 2, up to problem 5. The one that has SL1 requires you to do something with SL1 will already have SL1 in it. So you don't have to do any of that because that's not good use of your time during the exam. So what you will do just before the exam starts is you will run git pull to pull down the latest and greatest of the repo, and then you will have it. So if you've never done a git pull, God forbid, then now would be a really good time to do that, because you don't want to have to learn in the exam how to resolve conflicts. There should be no conflicts, but you never know. So make sure that you have done a git pull before. Don't put any midterm folder in there, because otherwise it'll conflict with mine. And then I will push everything, you will pull it, and after that you use no internet for anything until the end of the exam, and then you push what you have. If for whatever reason the internet does not work for someone, I will bring in a USB stick, and then we'll do it that way. Yes?
Will you be providing test cases?
I don't think so. I had no particular intention of doing that. And again, it wasn't really my interest to have you make it so that everything works. So if you want to test something yourself, it's easy enough for you, particularly for the first 3, where all you're going to have to do is just put them in a worksheet, and then you can run your own test case. And for the other 2, they read from standard input. So that I'll give you an outline that does the same reading from standard input that you've seen so far, and then you can just paste it in. Yeah.
Is there any form of way to look up Scala's libraries?
Yes. So what it says here is that you should download the slides and the Scala API before the exam. Someone said that this thing was broken. Yeah, okay. Oh, I need to fix that. Okay. If someone could remind me, then I'll fix that link, or someone could actually tell me what I did wrong. And so you should download those before the exam, so that you don't need to do that during the exam. So no internet during the exam.
Okay.
Yes?
I know this sounds weird, but on the exam, are we allowed to have this midterm practice sheet?
Yes.
Okay.
Yes, so it says here, you may put any files that you like on your laptop, including your My Homework and Lab Solutions, a letter from your significant other, and whatever you need for support. Yes?
Is that okay with a hard copy?
With a hard copy?
Like print it out? Or you cannot?
I guess. Whatever. I don't see how it's going to help you, but it would seem to me that if you wanted to search something, it'd be so much better off having it digital. Yes?
You said run git commit every 10 minutes. It's just, even if you have that's on average.
No, I'm going to say, every 10 minutes, I'm going to say, commit your work now. It doesn't matter what you commit, right? Git doesn't care if it works or not. It simply means that every 10 minutes, it's going to take a snapshot of what is on what is in your Git repository. Obviously, the reason for committing every 10 minutes is so that I can see how your work progresses from nothing to the solution that you're turning in. It's meant as a measure against cheating. It's very easy for the people in the back row to do something that I cannot see, but it's very challenging to come up with a plausible set of changes in a Git repository if someone else is in fact doing the work, right? So that's what it's for. It's simply so that I can kind of have a recording of your progress. Yes?
Do you have like a bash script for doing that? For auto-committing?
No, I don't have that, but I'm going to say, now is a good time to commit your work, and all you have to do is you run git commit-a-m.
Okay.
So I would just keep a window open, put in the command in there, and then hit up arrow every 10 minutes. You can do it more often than that. You can commit every minute. I don't care. Yes?
I was just going to ask if anyone needs help with Git. There's really quick commands you can use that will be appropriate for this.
Yeah, but in this case, I mean, the only command that you need is git commit -a-m.
Wait, does dash A automatically add all the files?
Yes.
Oh, I didn't even know that. I thought you could add dash capital A dot.
Oh, you know, I don't think that you need, in this case, to actually add anything, because I will give you all the files.
Oh, right.
That way, you don't have to mess with that.
Oh, okay.
Yeah.
Git add will save your changes too.
Yes. So this thing will, and all it will do is it'll change them on the local, on your hard disk. So if for whatever reason the network doesn't work after class, I will just bring in a USB stick and I will copy your entire repo onto a USB stick, and then that way I have all the changes as well. Yes, so really the only thing you need to do is this. I will give you a set of all the files. There should be no need for you to do git add. That way we keep it completely safe and eliminate hopefully all risk. But otherwise you could always say git add midterm.
Yeah, I didn't know about the lowercase a for git commit.
Yeah, I'm not a git master, so I can never quite tell you why you have to use this -a. My fingers.
Oh, because otherwise it only commits your added changes.
Yeah, whatever. My fingers type it without thinking.
But that's really convenient. I didn't know that. Cool. I need to read.
So really all you need to do is git commit every 10 minutes and you're done. And yes, I'm sure you could figure out the bash loop to do that for you if you put your mind to it. You could do a cron job.
What's that?
It's a job that gets executed every so often.
Yeah.
All right, so there were a couple of questions on Piazza. Like there was one person who said, with this alternating sum, how the heck do I do an alternating sum with recursion? And so I don't want to tell you how to do an alternating sum with recursion. What I want to tell you is the general recipe on how you can do anything with recursion. So I'm assuming that you know how to write a solution to whatever problem I give you in Java, right? Where with the alternating sum, you would probably say sum equals 0. Then you would have a sign. Then you had you would loop through all of the elements. And then you would say sum is sum plus e times sign. Sign is sign times -1.
That's simpler.
Right? That's how you would do it in Java. And you've been doing that long enough, you don't even really have to think about this. Now think about what you're doing. What you're having up here is the state. Oops.
What?
That's this little touchpad.
So,
Let me turn off the touchpad.
What? You can do that.
Yes. So this is more state. And then what you do here is you transform the state in each step. Right? That's really what you do in a loop. In each iteration of the loop, you get a new element in, and you transform the state. Now, let's do that with recursion. With recursion, you cannot transform the state because the state, you have no mutable state. So you have to now achieve this with immutability. So we're defining a function, alt sum. It takes a list. I'll omit the types right now in the interest of time. And then you're going to have a helper function. There's no other way, because any variables that you declare you couldn't modify, so you have a helper function and then you can mutate the parameters in each call. That's the general recipe. So I guess I need a brace here. So we need to define a helper. What are we going to call the helper?
helper?
H.
H.
It's an exam, right? You're not graded on style, so you give it the shortest identifier you can. It's hard to be shorter than H. I mean, I wouldn't call it underscore. It probably doesn't work. So it's a helper, and what does it take? It takes a list, and then it takes the state. Okay. Now, what is the state? Okay? And so, what is it? If list is empty, how do you test if it's empty? Is empty? It's something. Else, it's something else. Well, the else case, it's a recursive call, right? So you recurse in the tail, and now you do your transformation. The sum becomes sum plus e times sign. What is e as its listed head? And the sign is sign times minus 1. Okay? And if it's empty, what do you return? The sum, because that's now your final result. There you go. Okay? So nothing could be simpler. If you know how to do it with the while loop, you can do it with the recursive helper function. And that's true for really anything. You just figure out what is the state of your computation. Yes?
Are you going to have any bonus questions about Y combinators?
No. No. I've had bad experience with bonus questions on exams. So it is what it is. Yeah, by the way, you do not need to get a perfect score on every problem to get an A. Do what you can, and it will grade it on a curve. I've never given this particular exam. I have no idea how everyone is going to do, and so it'll come out the way it comes out. I mean, I have some idea of what the best students can do, but I'm not always right with these ideas.
I think I missed it, but did you just talk about the git push during the exam or git commit?
Yeah.
So I do that every 10 minutes?
Yeah. All right, so the next thing that I'm going to ask you to do is to do the same function with a fold. Now with a fold, it really is the same kind of thing. What do you do with a fold? You have the initial state. You have a value coming in. You then have the next state. You have a new value coming in. And then the next state, and so on. So let's see, what is our state in this case? Our state has two things in it. It has the sum and the sign. How do I store two things in Scala? With a tuple, right? So my initial state is the sum is 0, and the sign is 1. And then I combine that with the initial element, say it's a 1. Then afterwards, the sum is 1, and the sign is minus 1. And the next time, so let's say the incoming one is a 2. Now I have, because the sign is minus 1, I have to subtract, so it's 1 minus 2 or minus 1. I may make this a 3 so it's a little clearer. Then it's a minus 2 here, and the sign flips again to a 1.
Can we bring paper to the exam?
Yes, you can absolutely bring paper. And so if you want to sketch something, I will ask you to draw this fold tree for the fold, and if you don't want to type it out, you can just hand me in your paper at the end of the exam. For art, yeah, you can write out the entire exam on paper, but I mean, it's with the SL1 thing in particular, it's not going to be so useful, right? But yeah, if something is easy on paper, by all means, paper is your friend. So now, how we're going to now implement this? So with the fold, you always you have a seed value, which we now know to be 0, 1. This is a left fold. You might be presented with the right fold, so you might want to practice one of those. Then you have the list that appears on the fringe, so the list of the values that appear here. As we now know from CATSA, it's a good idea to put parentheses around this. Then you have the function that is the transformation from the state. So the transformation actually gets two things. It gets the state, and then it gets the incoming element. And now it needs to transform those to the next state. So I need to make a pair. The second one is the second part times minus 1. That flips the sign. The first one is So let's say you have to take the first one that comes in, that's the sum, plus e times the sign. Okay, so you can do it like that, or you can do, if you prefer, a pattern match with a case. So every fold works like that. You figure out what is the state transformation, and you program it. So practice that. To take an example where you might want to have a right fold, or simply try to do this with a right fold and see what happens, and so that you can know them both ways. The thing with the map and flat map, that is something that we had in the previous lesson. Let me find that. That was lesson 6. Yeah. So this was this thing where what you do to apply something to true lists. So we had true lists, and we wanted to have the combination of all of the elements in both and join them to pairs. And the question that we have here is kind of similar. You have true lists, and then you compute all of the differences. And the solution to do that is to use two maps, except you might want to work through this example one more time. If you simply take two maps, then you get a list of lists, and the flat map flattens it out correctly. So I would encourage you to go through this slide again, just do this on a worksheet, so that you can see how the map and the map works, where to put the flat map, and then try it out with this example. It's just a simple trick that you can practice. Now with these grammars, this is the grammar for arithmetic expressions that at this point I hope everyone has memorized. If I were to wake you up at 2 a.m. and make you write that grammar down, I hope you all can do that. And then you need to now say, okay, what are the changes that are required? In this particular case, we don't have minus. Well, that should be an easy change. We don't have a divide. That should be an easy change. But now we have to put in this bracket I comma j. And you need to figure out where do you put it in. And so, does it go between plus and star? Does it go below the star? Can you just add it on to that rule for the factors with the literals? So figure that out. Now, modifying SL1 to Booleans, you now know, or you will hopefully know by the end of today, how to add something much more complicated to SL1, namely lists. And so it's a kind of a similar thing. It's another data type. You have to worry about literals true and false. Now, you now know how to handle a literal nil, and true and false you could handle the same way. You have predefined functions and, or, and not. Well, you know how to handle predefined functions head, tail, and is empty, and so these would go the same way. And so this should hopefully not be much of a modification from that. Oops. I think I'm running out of steam here.
The recording is still on. No.
So, let me see if I can pull this up real quick. This is teach. This was SL, that's source. You are talking about this part here.
Yeah, why don't we just have like a fun call instead of?
Well, I don't like the parser to backtrack, and so this val or fun thing could be anything. It could be just a variable. It could be an expression that that evaluates to a function, right? You can store a function in a variable. You can have a function return a function, and so this thing could be anything at all that yields a function call. But I don't really know whether it's a function call until after I'm done with parsing it all, and then again, it might not be one, right? If it's followed by a parenthesis, it's a function call. If not, it's just a regular old non-function call expression. So what I do is I say, whatever this thing may be, and then it may be followed by a parenthesis.
But then, how do they differentiate that between just val or fun? Because
what the parser does is it will first call this function. It'll grab something whose value is either like an integer or a function, and then it'll try to find a parenthesis. If it sees a parenthesis, then it'll grab it. Then it will give you the parenthesis.
Off there, it doesn't need it, right? So how does it decide? So does it try like all combinations of everything?
Yeah, well, it won't. When you give it an opt, it'll try it, and if it sees a parenthesis, then it'll go ahead and parse it.
No.
So when there is a parenthesis, you can be guaranteed that that is what will be returned to you.
Okay.
It's not going to be coy about it and say, even though there was one, you said 0 is okay.
Does it always try and consume like the biggest?
Yes,
portion?
yes. So with an opt, it will try to make the opt happen. So that's, I guess, an important piece of information.
Because I tried to rewrite it and I couldn't get like the precedence to work out right.
Well, whenever you can't get the precedence to work out right, that may well be the case in this situation, then what's the trick to get to deal with that? So when you're in a situation where you want to parse the opt, and then you do it again repeatedly, right? But then you find that the precedence is just not working out right. Then the solution is to collect them all and worry about them later. So if you, instead of just optionally grabbing a parenthesis and then worrying about what might come afterwards, you can simply grab all the parentheses and then you sort it out. Then, of course, these cases here are going to be different, right? Because then if you grab them all, you're going to get a list of these things instead of an...
Like function call is really high precedence, right? So when I encounter like an identifier, if I want to...
I mean, this is a good point. This is a good place to do it. So think about grabbing them all here and...
Yeah, I did this one where I basically fumbled around where I put opt of reps in one.
No. You don't. This repsep has nothing to do with this. This thing here just grabs the arguments, right?
I have a opt represep one of all of that.
No. You want to have as many copies of this as you like. Arguments.
Yeah.
Okay. Someone explain this without giving the answer away.
Well, but I got it working thing, but the fast order thing.
All right. Well, there are multiple strategies of getting it to work, but the easy strategy is really to rethink how one can, instead of having 0 or 1, to have any number of at this point and then take it from there. And we did exactly the same thing in one of the other lectures. Must have been 6 after all. Nope, I have no recollection where this was. Oh, no, it wasn't parsing. What am I doing? It's on... Where was this where we grabbed all of the factors? Okay, I can't find it now. Put a question on Piazza if you're still confused, and I'll find the slide. So there was one slide where we said the natural grammar with the opt wasn't working out for us, and then we rewrote it to grab all of the factors. And the exact same trick works here. That's a useful trick to know, and that's something that there's two versions of the exam, and I can't remember which one you guys have, but there's one version where being able to understand this left versus right associativity of operators is really useful to have. Even for the homework, right? The colon is right associative. You want to understand that stuff. Okay, any other questions? Yeah.
So this is about the SL1, this is about homework 7?
Yeah.
Okay, so I have a question about parsing the list box. And it has to do with how we populate the initial symbol table.
Yeah. Now, where do you populate the initial symbol table?
I'm just feeding it in as like a predefined symbol table of tuples of a string and then list off.
That's what I did as well.
Yeah, that's exactly what you do. Like down here, where right now you have an empty list, you put in the one with the predefined definition.
Right, so I actually define it above that and I feed it in as a value.
Whatever, yeah.
Okay.
But my question is, when I do this, it parses the like, you know, the different list offs. But then instead of resolving them as list offs and then evaluating them as list offs, it resolves them as variables and then tries to evaluate the variable.
Right, and so when you evaluate a variable, what does it evaluate to? It evaluates to...
Its value.
Here is, yeah, exactly.
It looks at, yeah, it's a lookup, but then...
And now what it then has is now you have one of these list offs in your hands.
For some reason, I don't know why it was working. I had to replace nil, or like a list off with like L is just nil with just directly nil. Nil is...
Yeah, nils, yeah, that's fine. You define, I mean, nil evaluates to nil, the empty
Right,
list.
but it's not a list off.
No, it does. That one is not a list off. So there's
Okay, so it's
three of them are list offs, head, tail, and is empty, and nil is just nil.
Oh my god, okay, that makes sense. Because in your homework you said 4 list offs.
Well, if that is so, put something on Piazza and it'll change the wording.
You said 4 symbols, I can't remember.
Yeah, so it's 4 symbols, 3 of which are list offs, and 1 of them is the empty list nil.
I think it just says the 3 list functions.
Yeah, well, I know that just because it says that doesn't always mean that that's what people read, but, so if I did make a mistake there, let me know.
Okay.
Other questions? All right, then let's go and do the new lecture. So we're going to be talking about the functional language Scheme. Scheme is a dialect of the Lisp family of languages, and so all of these Lisp-like languages have like one characteristic feature, and that is their syntax. So they use parentheses for structuring everything. And so when you look at, for example, where it says here +3, 4 in parentheses, it's a list. Everything is a list in Scheme. The first element of the list is plus. That is the function that is being called. Everything else in that list is the arguments that are applied to that function. So +3, 4 evaluates to 7. Over here we have plus with more things, and then it evaluates to 24. Over here it computes the product of 3 applied to the sum of 4 and 5. This is wrong here, I need to fix it. So 4 plus 5 is computed first, that's 9, and then the answer is 3 times that, that's 27. So notice that in a language like Scheme, you don't worry about operator precedence because the operators are not written in infix form. The operator is always first, and so there's no question about precedence. Here we have an if operator. So if takes 3 arguments, the condition, the true branch and the false branch. So again, the operator followed by what it operates on. Here we have define. So define takes a list of two arguments here, where the first element of the list is the name of the function to be defined, and any other arguments in this list, here we only have one, are the parameters of the function. Then it is followed by the function body, which is again a list. So if it is true that less equal x and 1 holds, meaning that x is less equal than 1, then the result is 1. Otherwise, it's the product of x and the factorial of the difference of x and 1. So that's how you write it out in scheme. And you see the syntax is very regular. Here we're now computing the factorial of 10, and it is what it is. Finally, sometimes it happens that you don't want to evaluate a list. Consider the list 1, 2, 3. If you just put it into the REPL, the interpreter, then... So here's the environment, this Dr. Racket environment. It has two panes. The top one has definitions, and then the bottom one lets you run expressions provided that these definitions are in place. So anytime that you have it defined, you should put it on top. And then once you have it, then you should execute it. So I'm going to run execute. Now it runs this thing here with, this Lang slideshow thing is a little weird. It's meant as this educational environment, and they have a whole variety of different dialects of Racket with different parts of it activated and deactivated. The idea is if you give this to rank beginners, you want to make it so that if they use a complicated language feature, that it says it's outside your subset. So the slideshow thing has these elements to do this graphical stuff. So when we define what a circle is, and now you can actually see it. And so now the first question was, how do you get them on top of each other? And so you get them next to each other by running HC. No, I don't remember any of this. It's HC append, and then circle and the rectangle, and then they're like that. And so H means horizontal, so let's just try VC append. And then it puts them vertically. So that way you can do these little images. There was a question of the help, and the help gets you in this online help that I have here, and it then has a list of all of the various graphical appender thingers with a nifty little diagram here so you can see what they mean. Now on to the interesting part, to define our own functions. So we want to define a function that shows something n times. So where do we have it? So that circles n draws a row of n circles. So that we do on the top because all the definitions go on the top. So define circles. We have to put it in parentheses to show that we're defining a function, not a variable. Presumably it's a recursive definition, so if something... so if n is 0, then we want to have the empty list. I don't really know how to make the empty list. I'll just try to see if HC append of nothing will work. And I could just actually try this down here to see what happens. So this works just fine. I get a little warning here that says my definition have changed, but I'm just trying this out here while writing. So HC append of nothing seems to work, and otherwise it is HC append of a circle and circles n minus 1, which is minus n1. And now let me spread this out a little bit. So now as I hit the parentheses, you can see how these expressions are successively closing, so this seems good enough. So now I have this. Now I have to run execute again so that all the definitions are consumed. And now if I type circles of 100, then here they are. That's all. All right. So no, after the exam, you'll get a homework where you get to practice this, and of course, when you do it at first, you're going to not be quite as fast with these parentheses, but it's just a question of time before one's brains can automatically think that instead of saying n-1 to type minus n1. And whether you get to that time, to that level of expertise in this class, it's doubtful, but it doesn't really matter. The basic idea, though, is that you can see that everything in this program is just made up out of these lists, and that's what we want to use in the lecture after the break as a jump-off point. All right, so the other thing was, the lab wants you to look at some of these local definitions that are copied up here. So here you see a function checker that takes two shapes, that appends the first after the other, and then the other after the first, and then it puts them all on top of each other. So let me just try that out. Checker, a circle and a rectangle, and that gives you this checkery thing here. And of course I can keep on going. And then I get more complex shapes like that. Here, the point is that here is a local definition with a let. Right here it defines this P12 and P21 so that they're only used inside the body of the let, and afterwards the local definitions are gone. Now over here, it's almost the same thing, but notice that the let has a little asterisk in here. So what's the difference between let and let star? So you have to carefully look at the right-hand side. Here we're defining RP and BP. And then, as you can see from these lines that are being drawn in here, it shows that the definition of C uses what RP and BP are. Now, the way that let works is that it assumes for all of the right-hands that they only use symbols from the outer environment. So, if you just use a let and another let star, using the RP and the BP like that is not legal. And that scheme is different from SL1. In SL1, you could perfectly well use that because later definitions are allowed to use the values of earlier definitions. In Scheme, that's not the case. All these right-hand sides here must be coming from the outer scope. If you want to have the feature where you can define them a step at a time, then you use let star. Now, you could always use let star for the couple of times that we use Scheme in this course, and you'll be just fine. In fact, there's a third form called let rec that you use for recursive definitions. If, say, RP is defined by itself, or if you have a mutually recursive definition where the right-hand sides need to use each other. And so you could always use let rec in this course as well, and I think it would make a difference because we're not going that deeply into it. Let is presumably slightly more efficient, so people use the let star and let rec only when they have to, and it gives a visual indication to the reader, I suppose. So that's how you do local definitions, and that's pretty much all we need to know to do something with Scheme. So I will come up with an assignment, with hopefully simple and reasonably amusing assignment, where you can put this to work and just get some idea of what it's like. And then there's one big idea in Scheme, namely macros, and we'll talk about that on next Monday, Monday after our planning horizon. So exam on Wednesday, then we have spring break. Any questions about the homework or the exam? Put them on Piazza.
So we work in the exam director. Is that the same structure as like an SPT project?
Yes, I will make you an SPT project that has the SPT files, that has source main Scala.
Okay, and then we just do commit every time and it's not push? Or...
Yeah, because you're not supposed to be on the internet.
Oh.
Right? You can't push if you're not on the internet.
Oh, man.
But the commit will update your local data structures so that one can see the changes that you make. And then it's after the end, then I say, no, everyone should push. Okay? So, you may in fact say, well, if the syntax is so simple, why don't we just teach Scheme to freshmen? You had a question?
So is this considered prefix notation? But the second
Yeah.
line isn't really prefix notation, is it?
Let's see, this is prefix? Which one do you say is not prefix?
Plus 3, 4, 7 is fine, because you would need more pluses for that, right?
Oh, well, the plus function in Scheme can take any number of arguments.
Okay, so it's a variable argument.
Yes,
Okay.
yes, absolutely, yeah. So you may wonder, can one teach this to freshmen? Because they don't have to learn any syntax, right? And so the answer is absolutely. There's some universities where they use Scheme as the introductory programming language for that very reason, that there's no syntax to teach. Once you get the idea of the parentheses, everything else is the same way. And you can't really say, well, I got a syntax error, right? There are no syntax errors as long as the parentheses are well formed. The problem with teaching Scheme to freshmen is that on day one, you show the slide, and on day two, then you start getting going with some actual algorithms. That's before the drop deadline. When you teach Java, you have weeks of showing how the IDE works and how the syntax works and what variables are and what a for loop is. And by the time that you get to loops and arrays, where students really struggle, that's well past the drop deadline. And so you still have students in your course. So that's the only disadvantage with teaching Scheme is just like JavaScript. It's dynamic, and unlike Scala, it's dynamically typed. So here I have defined a variable x as 1. Notice, by the way, the difference between defining a variable and defining a function is that when you define a variable, there's no list here. It's just a single thing. With a function, it's a list consisting of the function name and the parameters. Yeah?
On the third line, big block there, it's confusing how you have the...
No, this is wrong.
It is?
Yes, it's wrong. Yes.
Okay.
So, yeah, I said that, and I really need to remember to fix that slide. Yes, it is 3 times parentheses 4 plus. Absolutely. So, all right, back to this. So we're defining a variable x, and we're setting it to 1. In Scheme, you can mutate things. It's not really something you necessarily want to do often, but it's just like in Scala. And the mutator is called set exclamation mark, and the exclamation mark is supposed to make you pay attention. And this is an unusual thing. So here we're setting x to be now the list 1, 2, 3, and in Scheme that's perfectly fine. So x can hold a variable of any type, and then you can later change the type, just like it with a variable in JavaScript or Python. It's a functional language, exactly like Scala, and all the same concepts apply. Here we're using, for example, map. We're mapping a function to a list, and that means that each element of the list is transformed by the function. Let's see what the function looks like. It has the funky symbol lambda in front that I'll talk about in the upcoming slide. That means it's a function. Here's the list of the parameters, and here's the body. It multiplies x by itself. So by applying that function to 1, 2, 3, then we apply it to 1, which stays the same. 2 becomes 2 times 2, 3 becomes...
Oh, it says lambda calculus.
Yes, it's the same lambda as from the lambda calculus, absolutely. So in Scheme, we would write it slightly different. We would write x colon int and then the fat arrow. And so here, instead of using the arrow, it uses that funny symbol lambda. It uses it for historical reasons. So a bit of control flow. That the if statement you already saw. We have if, condition, and then expression 1, expression 2. Then ands and ors if you need them. And there is a thing called a con that's often useful in practice. It really is the same thing as like a nested if-else, but it's a little bit shorter. So if the first condition applies, then the first expression is the value. If the second condition applies, the second expression, and so on, with an else for default. So you can think of that as the equivalent like of a match, and it's not, except it doesn't do pattern matching. It simply evaluates the conditions. Now, because there's now an awful lot of parentheses, what some people like to do is for these pairs of things that they use square brackets. In Racket, you can use any combination of square and round brackets, and that makes it a little bit easier to see the matching parentheses. So here I have an example. I have a con. If x is less than 0, it's minus 1. If it's equal, then 0, 0. Otherwise, it's 1. So that would give you the sign of the value x. Then there is a let that you can use to make local variable definitions in a block. And it's exactly the same thing as a block in Scala or in SL1. So we have variable definitions and then in the end some expressions. Because in Scheme, expressions can have side effects, which it supports multiple expressions. In SL1, where we don't have side effects, that wouldn't make any sense because only one expression can really produce something. But so here you have a sequence of expressions in the let statement. So this means that the variable 1 is defined like this, variable 2 is defined like that, and with those definitions, you then evaluate these expressions. The value of the let is the value of the last expression in the chain, exactly like it would be in Scala. So the syntax, I think, is clear enough. Again, the parentheses is a little awkward, that the let is followed by a list, and that list now contains more lists, and these short lists, again, people sometimes put square brackets around it to make it easier to read. But some people don't, so you have to be able to read it either way. So here are anonymous functions. We use the word lambda from the lambda calculus instead of like the word function as you would in JavaScript and the fat arrow as you would in Scala. Yes?
How can you type a lambda?
So yeah, if you for some reason have a keyboard that doesn't have a lambda, then there's two ways. In Linux, it's really easy because you can add any number of keys to your compose configuration. And so in my Linux system, I did it so that when I type a special key followed by G and L, G for Greek, then it types a lambda. So if you use Linux, that's highly recommended. And I use that for accents and for all sorts of other things, like for arrows and copyright symbols. It's a very useful thing. So you have to nominate a key, and I use caps lock, which I never use for anything else. But you can use one of the other less useful keys on your keyboard for that. Unfortunately, that doesn't work on any of the other operating systems that you may have, which is kind of sad. In the Racket environment, as it happens, you can just hit Control / and it gives you a lambda. And you can also type out lambda as LAMBDA, which will always work, but is of course uncool. Yes?
Can we select a different key?
No. And it has to be either the Unicode lambda or it has to be the word lambda spelled out in English. Yes?
You can also use alt codes. So alt plus the code.
Oh yes, that probably would in fact work. So you can use alt and then type out the Unicode. Does it work with Unicode?
It should.
Yeah. Yeah. I don't really know. I mean, when I was in college, I had a couple years worth of Chinese, and one person there was a telegraph operator and knew all the 5-digit telegraph codes of like 100,000 Chinese characters. So it was very impressive. So if you have that kind of memory, then that method will undoubtedly work as well. But I like the compose ones because you can come up with some mnemonic ways of remembering these things. So if you do use Linux, check out compose. If you don't use Linux, forget it. All right, so those are anonymous functions. And the syntax, you just have to have a cheat sheet and just map that mentally to what you would do in Scala. In Scala, you would just have a fat arrow and not the lambda. Yeah, why the lambda? Because in the lambda calculus that was invented by Alonzo Church, he based his notation on an older mathematical work where they used an uppercase lambda. And for some reason, he made it lowercase, or I don't really know why. But ever since, we have this lambda for anonymous functions. And of course, even in Java 8, one calls these things lambda expressions. Though Java, for some reason, did not have the courage to use the letter lambda. So there's two kinds of definitions. We talked about that already, variable definitions and function definitions. These are just added to the current scope and then are then globally visible. And you can use let for local definitions. And we'll look at let in the lab for a few minutes. Lists are just like you would imagine. They're written in list notation, of course. You have three functions: first, rest, and cons, that are the same thing as head, tail, and colon, and stop. So now here I have a list. First returns the head, rest returns the tail, exactly like you would imagine. And cons is used to put a head and a tail together to a larger list, exactly like colon. So here you get generic list functions. We had exactly the same slide with Scala a few weeks ago, where we have like a typical list function that sums up all of the elements of the list. So we were defining the function sum, whose single parameter is a list. If the list is empty, then the result is 0. Otherwise, it's the sum of the first element in the list and the sum of the rest of the list, followed by a whole bunch of parentheses. Now, if you want to build up a list recursively, you use cons. This is a list of squares. So it's the squares of all numbers up to the number n. If the number n is 0, then it's the empty list. And otherwise, we stick together the square of n followed by recursively by the squares of n minus 1. So if we compute squares 10, then we're going to get all of the squares from 1 squared to 10 squared. Which one are we going to get at the front? 10 squared or 1 squared? Squared, yes. Because when we compute squares of 10, it's not 0, so we're making a cons of 100 followed by something else. I'm not even going to think what something else is. I know there's 100 in the front. All right, so that's all we need to understand how Racket works. So go ahead. If you haven't done it already, just install Racket and get going with this little mini tutorial. And spend 15 minutes on it, and so they get a feel for what the environment looks like, and then we'll go over it together.